Hi, my name is Dr. Jonathan Fairman, and I'm the principal modeler behind Build Your Own Earth. I'm going to talk to you today about how to use Build Your Own Earth as a tool to explore the climates of the Earth's past, which we refer to as paleoclimates. When we discuss a paleoclimate, we need to consider several factors that may influence the temperature and rainfall patterns that potentially could have existed at this time in the past. Differences in greenhouse gas concentrations, continental configurations, and solar energy are some of the major factors that could cause the Earth's climate to change. The Earth's past temperatures have varied quite a bit from the current day throughout the Phanerozoic. For example, 21,000 years ago at the last glacial maximum, temperatures were several degrees cooler than they are right now, as we can see on this graph. Throughout most of the Earth's history, however, temperatures have generally been warmer, sometimes very much so, such as during the Jurassic, when temperatures were around 5 degrees warmer than today, the Triassic, where temperatures were up to 10 degrees warmer than today, and the Cambrian, where temperatures exceeded 12 degrees warmer than today. For Build Your Own Earth, we have run 10 different paleoclimatic simulations: the last glacial maximum, the Miocene, the Cretaceous Tertiary boundary at 65 million years ago, both pre and post an asteroid strike, the Jurassic at 170 million years ago, the Triassic at 240 million years ago, the late Permian at 260 million years ago, during the Carboniferous at 300 million years ago, during the Cambrian, the late Cambrian at 540 million years ago, and the Ediacaran at 600 million years ago. These times have been chosen to provide snapshots of what past climate states could have been, using reconstructions of past greenhouse gas concentrations to try to determine if we could reconstruct the specific climate that would have resulted. Greenhouse gas concentrations are only one major difference that the Earth had in the far past. The continental configurations, as well as elevations at various locations, were quite a bit different as well. What we're going to do is look briefly at the various maps of topography for these ancient Earth simulations and try to think how these may impact the global climate system in terms of ice and ocean current formation. Let's look at one ancient Earth in particular, the Triassic simulation, where the supercontinent Pangaea would be the dominant feature. If we look at the land and then surface topography, we can see that Pangaea is centered upon our prime meridian, with the shallow Tethys Sea to the east and the wide open ocean of the Panthalassic Ocean to the west. The rest of the continents are all grouped together in the center. The Triassic period has greenhouse gas concentrations around 7 times more than today, so we would expect it to be much warmer, which, if we take the global average from this simulation, it is by around 5 degrees. Okay, let's look and see how the ocean currents change when we have a shallow sea and deep open ocean. If we go to ocean currents, high vectors, and look at the surface currents, we can see that over the Panthalassic Ocean, we have a very strong easterly equatorial current that breaks up as it encounters the shallow Tethys Sea. This prompts a seasonally varying returning westerly current, which we can better see if we switch our views from the prime meridian view to the 180-degree view. This returning westerly current is strongest during August through October. So as we look through these different months, we can see how this warm water would have been moved to the west. If we compare these to the Earth of today, we can see that while today's Earth has this strong easterly equatorial current, as does the Triassic, the seasonally varying westerly current is in the southern hemisphere in today's Earth, where it is in the northern hemisphere during the Triassic. There is also quite a bit more poleward motion in today's Earth compared to the poleward motion found in the Triassic. If we look at the sea surface temperatures, we can see that the warmest water would be found in the Tethys Sea, where sea surface temperatures exceed 34 degrees. These would prompt very strong tropical storms impacting the coastlines of the northern Tethys Sea. Another interesting feature of the Triassic that we can determine by looking at the sea surface temperature is that there is very limited ice cover over the North Pole, where you have a very small amount forming just to the north during January and February. This is starkly different to the cold temperatures and sea ice formation that we would see on the Earth of today, where you have a permanent sea ice feature that expands in the winter and then declines during the summer. You can also see that the temperatures are much warmer at the North Pole and in the northern hemisphere during the Triassic simulation. This is due to the easterly equatorial current of the Triassic forcing this warmer water further poleward because of the continental configuration. If we look at mean surface temperatures, they follow a similar pattern as the sea surface temperature. A permanent desert would exist between the equator and 30 degrees north over Pangaea, as temperatures would routinely exceed 40 degrees during the summer. This desert feature would also be present in the southern hemisphere. The poles would get cold in the winter, but mainly just the South Pole that would have average surface temperatures less than minus 20 degrees because of the strong continentality present in the center. It's very far away from any of the oceans. The North Pole would get a lot cooler over the winter, but just over the continental area, the oceans would stay fairly warm. If we compare this to today, we can see that there is quite a bit of a difference in average temperatures, with the poles staying fairly cold during today's simulation, whereas only the South Pole having a large seasonal variation during the Triassic simulation. Precipitation during the Triassic would be dominated by a very strong intertropical convergence zone, with permanent deserts found to the north and to the south of the equator. A monsoon-like pattern settles in on the northern Tethys Sea, with the months of March, April, and May being almost as dry as the desert areas, and the months of July, August, September, and October being very wet as the intertropical convergence zone moves to the north. These changes in precipitation seasonality would also impact the sea surface temperatures that we have seen before. Comparison to the current day shows that not only can the Triassic ITCZ be a little bit stronger than the ones that we have today, but that this formation of this second desert area south of the ITCZ is present during the Triassic, yet not in the current day simulation. I hope that you have found this demonstration of the Triassic period interesting, and that it proves useful as you explore other ancient Earths, considering both the changes in greenhouse gas concentrations as well as the changes in paleogeography. Let us know in the forums if you have any further questions, and happy exploring.